Good day, everyone. This is Imran. I am an AI technical solutions specialist with Intel. In today's session, we'll be looking at how to get high performance, low latency inference for transformer based NLP models on cloud. So we'll be using cloud instances running latest generation of Intel Xeon CPUs for this demo. We'll see how to get this high performance with the help of Onyx models that have been quantized using Intel Neural Compressor. It is true that training a big model requires a lot of compute resources. However, for productionized models, majority of compute cost, in fact, about 90% of the compute cost is attributed for inference. To get this cost down, it is essential that we have the fastest possible model deployed in the instances with lowest possible uh, cost associated. That this again is without the compromise of the performance metrics of the model. So that's what we will be seeing on how to use ONX and Intel Neural Compressor to achieve this target. So ONNX is an open format built to represent machine learning models. It defines a common set of operators and a common file format to enable use of models with a variety of frameworks, tools, runtimes, and compiler. It was developed and maintained by a community of partners, including Microsoft, Facebook, and AWS. It supports interoperability of models between different frameworks like PyTorch, TensorFlow, MXNet, to name a few. Onyx Runtime is a cross platform inference and training machine learning accelerator. Onyx Runtime Inference can enable faster customer experiences and a lower cost, supporting models not only from deep learning frameworks like PyTorch or TensorFlow or even MXNet, and it also can work with the classical machine learning libraries like scikit-learn, LightGBM, XGBoost, and so on. So, like we saw earlier, we'll be running this demo on an instance hosting the latest generation of Intel Xeon CPUs enabled with DL Boost. Intel DL Boost Vector Neural Network Instructions, in short VNI, delivers about 3x performance improvement by combining three instructions into one for deep learning computations. So this directly helps in reducing the memory bandwidth and maximizing the compute efficiency and cache utilizations. The example that you see here, where the weight and the input tensor gets added and it gets converted onto 32-bit. So this 32-bit output is again added with the bias of 32-bit to get the final result, right? So this process that takes 3 steps to complete in a regular AVX 512 instruction set will take just 1 step when VNNI based instructions are used. So we will be quantizing our Onyx model, which uses the VNNI optimizations, which is available in the Intel Xeon 3rd generation processors. So like we said, this demo will use Intel Neural Compressor. Now, what's an Intel Neural Compressor? It is an open source Python library supported on Intel CPUs and GPUs. This delivers an unified interface across multiple deep learning frameworks like TensorFlow, PyTorch, Onyx, and MXNet. So again, where it uses different types of compression technologies like quantization, pruning, knowledge distillation, and all this is available as a straightforward simple API. Right. It also implements different weight pruning algorithms to generate prune models with the predefined sparsity goals. You also have knowledge distillation to do a teacher-student knowledge distillation, And specifically in this demo, we are going to see the post-training dynamic quantization. So post-dynamic quantization, just like the other quantization techniques that is listed over here, uh, will convert the weights from FPW to int 8. Uh, However, specifically with dynamic quantization, we are also converting our activations on the fly to int 8. Again, this is just happening just before the computation is being performed. So the computation is actually being performed using the efficient int 8 matrix multiplications through the VNI that we saw in the earlier slide. Again, point to note here is that the activations are read and returned to memory in floating point format. So moving on to the demo. So let's get a brief overview of what we are going to do in this demo. So what we're going to do is we're going to load a model, a full model, a 6-layer model, in fact, and we're going to take that model of FP32 model, then we're going to prune some layers of it, essentially deleting the top layers of that 6-layer model. Then we're also going to load the data set. We're going to fine tune our models, both the full model and the pruned model, with that specific data sets. And once we've done that, we're going to convert it to ONNX FP32 model for both the full model and the pruned models, right? Then we're going to run a benchmark, which will calculate the speed of inference and the accuracy of these two models, so that we get a perspective on how good or bad these models are, both the full and pruned models are, in terms of the speed and accuracy. So to start off, we are going to use a cloud instance. So the cloud instance that I'm connected to is from AWS. It's M6i instance. It's got about 4 cores, 4 virtual CPUs, and about 16 GB of RAM. And we want to show that we make sure that we monitor how the core utilization is while the process are getting executed. To do that, we're just going to start off this htop command, where each of these bars indicate the utilization from a core's perspective, right? So this is about the instance. So to start off, the first part, like we said, we're first going to load the full model, prune it, then run then fine tune it, and then finally run benchmarks on top of it, right? So that's what we're going to do. We'll start off with the imports. Like we saw earlier, we're going to use Onyx, and we're going to use the transformers library and the dataset library to load and train the models. We are also going to use Onyx runtime, not just to run inference, but also to convert our Onyx models to quantized models, Onyx quantized models, right? So these are the imports that we do. And here we're going to restrict that. We just want to use 500 samples from our train and test set. So the model that we're going to be using is from Microsoft. So this is a distilled approach. MiniLM is a distilled approach that have been created by the researchers at Microsoft. So the original paper, it talks about 3 different types of model, if I recall it right: a 12-layer model, a 6-layer model, and a 3-layer model. The researchers have been generous enough to upload the 12-layer version of the model on Hugging Face Hub. So what we'll be using is a 6-layer version of this 12-layer model, wherein every alternate layer has been removed. So this is the model that we're going to be using for our benchmarking activity today. Coming back to the code, so we talked about the model. Let's go ahead and load the dataset. So the dataset that we're going to be working with is the IMDb dataset, a sentiment classification dataset. The data has already been loaded from the cache. We're going to use the same tokenizer that comes with the model. And we are specifying that the maximum sequence length that we want our models to be trained at would be 128, right? And we specify the parameters for our tokenizers, then we tokenize our datasets. So once we have the tokenized datasets, we're going to randomly select about 500 samples from each train and test, and we're going to save that in the variables a train eval and a train dataset, small train dataset, and small eval dataset, right? So that's what we're doing here. Then we are loading the model, and we're going to specify the labels as 2 because it's a sentiment classification dataset, right? So what we're going to do next is we're going to create a small function which prunes the layers. So this function takes inputs of the model and the layers that needs to be retained. The model will be copied, and the copy of the encoder of the copied model will be replaced by this thing called module list. And what is this module list? It's nothing but just a small fraction of the original encoders, where we just take the first n layers to be added to this new module list, right? So that's what we're doing here. It's a small handy function, and we're going to create our prune model by passing our original model that we saw in the earlier step, and we're going to say that we want to just save and to effectively keep just 2 layers to it, right? So next we create a function. We create a function to compute the accuracy metrics. So this is going to be passed on to our trainer. We also specify the training arguments, as in the number of epochs that we want to train. We want to train for close to 20 epochs. The batch sizes to train and validation batch sizes are going to be 32, and the evaluation strategy is going to be steps, right? So I'm just going to specify these arguments. Now we're going to go ahead and train our unpruned full model. So we just got to wait for some duration till the training gets completed. Okay, the training is completed. What we can see here is that there is a slight overfit of the model. And the best possible accuracy that we got is close to 75.4, right? And now let's go ahead and fine tune our prune model, 2-layer prune model. So point to note is that like we saw here earlier, we are just retaining 2 layers from the original model and just discarding the rest of them. And for that matter, since there is a copy function, a deep copy function, which is embedded into this data encoder layer function, there are not going to be any shared weights, as in the training that's been done to this model, the full model is not going to be affecting the pruned weights of the pruned model. Okay, so now the prune model is also being trained. Again, we find the same behavior, that despite the overfit, we find that the maximum best possible accuracy that we got on the validation set is close to 77.2%, which beats the numbers that we got over here. That is 75.4. So clearly the 2-layer model is giving us better numbers in terms of accuracy, at least. Now we're going to see how the model performs from an ONNX perspective. To do that, first we have to export the model to ONNX. We've created a small function here which takes the inputs of the model and the path where the file has to be saved, the converted ONNX file has to be saved. So the input model is placed to CPU, then again it's placed in the evaluation mode. Then we create a sample of inputs that's intended for the model, the input IDs and the attention mask. We pass the model and the inputs to the torch.onx.export function, which saves the model in the ONNX format in a specified location. So let's create this function and let's save both the full model and the prune model. So next, to run the benchmark, we want to convert our evaluation dataset into the PyTorch format, and we're going to do that by setting the type as torch over here. And the actual eval dataset, it has the one other column called text. We're going to discard that since it's not needed over here. So we're just going to retain the label, input IDs, token type IDs, and attention masks. So that's what we're going to retain. So let's create this, or rather update this eval data set. Then comes the run benchmark function. So here we pass the model, the data set, to this function, which creates an open Onyx runtime using the model inference session, using the model that we've passed on to it. There are some placeholder variables for counters, as well as a bunch of empty lists that we will be using in the function below. The data that we are passing to the function is loaded as a Tosh data loader, and if we wrap it with the TKDM so that we can see the progress bar. So we load the file. Point to note is that the batch size that we are working with is just going to be 1. Yeah. So now next we enumerate the data loader, and we load the inputs, the masks, and we're going to convert it in a format which can be used along with the Onyx runtime session, right? So we convert it into this dictionary of numpys. Then we pass it on to the session to get the outputs as ORT, right? So only this part where the data is loaded and passed on to the model, that only that part is timed in this function. We also get our labels so that we can use them to compare it with our prediction to get the accuracy, right? So we get our predictions, we get our ground truths, which is being appended to these lists of predictions and GT. And what we have here is that we want to make sure that the timing starts only after first 20 inference points, right? So this is to ensure that there is some sort of a warm-up available. So after the 20th data point, the timings are going to be calculated, and we're going to find the difference between the start and end, and the difference is going to be multiplied with 1000 and is going to be appended to this empty list that we saw earlier called hist. And we take the final list, which is named as hist, and we're going to find all the different values of, in the numbers, and the mean, the standard deviation, the minimum maximum values, the medium, the 95 percentile, and the 99 percentile. All these values we're going to print out. Also, we're going to compute the accuracy, and we're going to return the accuracy for when this function is called. So this function serves two purposes. One is to get the accuracy and the inference time. And second, we are also going to use this run benchmark function along with our Intel neural compressor, which is going to serve as an evaluate function to see how good or bad the quantized model performs. So that's what we're going to create this function. Then we're going to run the benchmarks for our unpruned data, as well as unpruned model, as well as the pruned model. So what you can see here is that the average time that we got is close to 15.84 milliseconds, and this is for a sequence length of 128, right? And the standard deviation is about 2.83. The accuracy, at least for the weights that was loaded when this Onyx model was created, is about 74.6. Now for the pruned model, we see that the timing is drastically reduced from 15.8 milliseconds to 5.6 milliseconds. And here the minimum value is close to about 4.82 milliseconds, right? So clearly the pruned model is outperforming the full model in terms of the speed. Again, this numbers that we are seeing is for the 480 data points, with the initial 20 being skipped for the warm-up steps, right? So this takes us next to the second part of the demo. So next, what we're going to do, the part 2 is we're going to take the prune model. We're going to quantize this prune model using two different techniques. One using Intel neural compressor, and other using the default configurations available through ONNX. And we're going to take both of these models and see how good or bad these models are in terms of speed and accuracy. So let's go to the code now. So to start off, we create a small function to quantize our data using the methods that's available through Onyx. So we the model that's going to be passed to this function is going to get loaded, is going to be checked by the check model function in the Onyx library. Then we're just going to convert all the weights from FP32 to int8, and we're going to save it in this specific location, which is passed as a parameter to this function. So let's go ahead and do that. Create the function. So let's go ahead and quantize the pruned model. And the benchmark, what you can see is, again, the number has been drastically reduced from 5.6 milliseconds to close to 3.24 milliseconds. And you can also see the drop in accuracy. The original FP32 model was 76.8%, and this model that we have, the quantized model from default Intel Neural, from the default options available through Onyx, it is at 76.6%. So there is a 2 percentile drop effectively in terms of your accuracy. And let's see how we can get that fixed with the Intel Neural Compressor. So to give an overview on how the quantization workflow happens, first the FP32 model is going to be passed on to the quantizer. So it's going to be calibrating it as in identifying what accuracy, rather the evaluation metrics in this case is accuracy. So what accuracy is being observed in the input FP32 model, right? And this is going to be in accordance with the data set, which is also going to be passed as an input to the function that we're going to create for quantizing, right? So once the baseline is constructed, baseline accuracy is constructed, then there are going to be a default set of configurations for quantizing the model. So the weights get converted to int8. Then the converted int8 model is going to be passed on to the same evaluation function. This evaluation function is going to run the metrics check again. So it is going to see if what the criteria that we've specified for the quantizer configurations are met in terms of the thresholds that is permitted to be compromised in terms of the accuracy, right? The evaluation metric. And if it does meet the thresholds that we've set, then now it'll just output that quantized model. If not, it'll go ahead and figure out other set of configurations based on the tuning strategies that we give to find the best set of partial set of weights, I would say, which can be retained as FP32, and the rest which can be converted to int8. And there is also other bunch of optimizations that goes on behind. To put it in very simple terms, it iteratively tries and finds the best set of configurations for your FP32 model, which can be converted onto your int8 model with the goal of meeting your accuracy, right? So that's the whole workflow of how the quantization works with Intel Neural Compressor. Now moving on to code. So the configurations, if you look at it, there are like 3 categories. One is the model configuration, second is the quantization configuration, third is the tuning configurations, right? So in the model configurations, you specify a random name. It could be of any choice of yours. You also need to specify which framework you're working with. So these frameworks could be PyTorch or IPEX or Onyx runtime, or even MXNet for that matter. We also specify which device the configuration is targeted for, right? So this is the first set of configurations. The second set is the quantization. So here we specify that we want to work with post-training dynamic quantization. Again, there are other methods available, as we saw in the earlier slide, which talks about static quantization. You also have another option of quantization about training. Now, third set of configurations that we have here are the tuning configurations. Here we want to set the thresholds, as in what is the limit that is acceptable in terms of the compromise that we are willing to take in terms of the accuracy, right? So here in this example, that what we see here is that we are allowing a relative drop in accuracy of 1% when compared to the FP32 model. So that's what is being specified here. The exit policy determines when to stop the tuning. So here, when the timeout 0 indicates that if we want to stop early, and here the max trials number indicates how many the loops that it has to try out till it finds the best configuration, right? That's set, and it also sets the random seed to ensure that you have deterministic tuning happening in your loops, right? So that's what these configurations mean. Coming back, from a model configuration standpoint, we are just keeping a name as BERT. The framework here, since we are going to be working with ONNX inputs, we are specifying it as ONNX integer ops. The quantization, again, the same post training dynamic quantization. Again, the same set of configurations that we saw for tuning as well as in the slides, right? Here we have said that the relative percentage that we want to that willing to compromise is like 1%, and this is what the file is. So let's go ahead and write this file. Next, we create a small function which takes the model saved path, the ONNX model saved path, the path of the configuration file that we just saved, and this save path is the location where the quantized model has to be saved, right? And we also have another parameter called tolerance, which can control this value, this relative tolerance value, which is like what we specified as 1%. We can keep it as 10, right? The default we default it for 10. So that's the input parameters. So we load the model, and we also load the configuration file set as the variable of quantizer. We modify the tolerance to 0.1, which is like 10%. Once that's done, we set the additional parameter for a quantizer, which is the model, the tokenizer, and the eval function. So eval function is the same function that we use it for the benchmark, which gives us the accuracy as well as the statistics for our inference times for various numbers. So we set all these values for the quantizer, and we call the quantizer. We save the output to the variable q underscore model, and that variable is going to be, which contains the optimized set of weights, is going to be saved to the save path. So that's what we are doing here. Now we go ahead and we convert the model, the prune model, to a quantized version. So what we see here is that first it runs the baseline, right? The accuracy of the FP32 model is 76.8. Now, based on that value, it tries and figure out the different set of weights that we could get, right? So here, fortunately, even the first trial itself, we got a better set of weights, which is about 77.8% compared to the FP32 model, which is like 76.8%. And in fact, this quantized model, the interneural compressor quantized model, outperforms in terms of accuracy from what we saw over here. Yeah. So here the quantized model that we got from the default ONNX is 76.6, which is lesser than 76.8, 2% lesser. So here we got no more number. We got 77.8. So now let's go ahead and run the benchmark. Let's see how fast the model runs. So the model runs at 3.2 milliseconds on average, almost slightly faster than the ONNX quantized model, or rather I should say the model that was quantized from the default configurations available from ONNX, right? So that we have that. So there could be cases where where you might want to have a little bit more tolerance, right? So that so we can control, say we don't want to have 10% drop. we don't want to accept 10% drop, and if we just want to retain the same performance as the original FP32 model, we can specify it as 1% here and run the whole process again. But since we got lucky and we got better number than our FP32 model, we're not going to be running this code now. So next step is just a simple step where we take parts of the code that we saw in the top, and we're just going to write into this file called benchmark.py. The imports, the data set, the pre-trained model, the tokenizer, all the variables needed, then the function to tokenize. Then one major difference over here is that we are selecting about 3,000 samples instead of 500 samples that was used during the training process from both training and evaluation data sets. So we're going to run our numbers for 3,000 records and see how fast it is. Then now we also copy paste the run benchmark code that we saw in the earlier step. So this is effectively what we are doing. And here one change is that we are converting we are updating the warm-up steps from 20 that was the original code to 100 over here. So rest all these things are just same. So let's go ahead and run the code. So what we are doing here is we are using something called NumaCTL, which helps with pinning the processes to specific cores. So here 0 and 1 indicate the cores 1 and 2. So we're going to see that only these two cores are going to be utilized when we run the code. So this ensures that the process runs as fast as possible in the allotted cores. So that's what we're going to do here. And let's just run it. So data set is being loaded, and here you can see that both these are cores are running and they are in green, meaning they are efficiently utilized. There is no sort of lag happening in the backend. So what we getting here is close to 3 milliseconds. So again, for the sequence length of 128, we are getting about 3 milliseconds just on 2 cores of the latest Intel Xeon processors, right? And again, despite that we have taken 3,000 records and we just trained it for 500 records, there is a relatively less drop in terms of accuracy. Again, the accuracy is remaining about 76%. So there is no change there. But for some matter that you choose that you don't want to work with a batch size of 128, but you are satisfied with just working with the batch size of 16, you can also do that. And we'll see there could be some scenarios where you might want to use this, right? So, and given that you have such scenarios, if we run the benchmarks, let's see how fast our average time comes to. So again, both the cores. So here you can see that the mean is like close to 0.6 milliseconds, right? Which is just like quite decent, where you have requirement that requirements where you have to have less than 1 millisecond inference speeds, right? So this is something that you could use. Obviously, there is drop in accuracy, right? Because the model was trained with a sequence length of 128, and here we're just using the sequence length of 16, right? So be it sequence length of 128 or be it the sequence length of 16, we saw that the quantized model, the Intel neural compressor quantized model was blazing fast, right? So this will help you in saving the cost, and it also without compromising in terms of the speed and accuracy that is wanted of your model. So in summary, we saw how we can take a model and train it for sentiment classification task. And in fact, we've taken the model, we've pruned it, we reduced it to just have for 2 layers. And we saw that the 2-layer model was equally performant as that of the 6-layer model. And when we used Intel neural compressor, the dynamic quantization actually enhanced the accuracy on our validation data set compared to the base model. And we also saw how now varying the sequence length that we were able to get exceptional performance. That is, for sequence length of 16, we got about 0.6 milliseconds on average, and for a sequence length of 128, we got close to 3 milliseconds. So this is how you could use Intel instances on cloud to make blazing fast inferences. Thanks everyone.